So essentially, the exercises for week 6 are not hard at all. The main challenge lies in being able to comprehend what you're supposed to do in the assignments, because there is a lot of text. And the thing is, you need to be able to read this correctly and quickly get an overview of what's going on. And this is something that we practice in general, so it's also good that we do it here. So let us read the assignment text for assignment 6.1 together. We are asked to consider a PDE of this form here, where you see there is some partial derivative with respect to t and with respect to x, and some constant functions that are involved. And we're told that this is a parabolic PDE, and that has something to do with the way these coefficient functions are given. And we get a terminal condition and some boundary conditions. So whenever we are introduced to some kind of finite difference method that we use to solve any differential equation, there are two questions we need to ask ourselves and answer. One question is, what's the grid? So incorporated into this question is, stuff like which domain are we interested in solving this differential equation on? How do we draw a grid on this domain? Which points are we going to make finite difference approximations of these derivatives in? Etc., etc. And the second question is, what do we know? Because normally with differential equations, you are given, some kind of boundary condition or initial condition or certain coefficient functions that we know, and it's a good idea to just list up everything that you are given already in the beginning, because especially in this week we have lots and lots of different Greek letters that we have to that we have to use in our calculation. So it's good to know stuff like what we know and what we want to find. So we know what we want to find. We want to find the solution f to this differential equation, but it's just as important to list up what we can use if we want to find f. So the first question, what's the grid? Well, we are told that there is a terminal condition at time big T, so we have T over here, and this terminal condition is given by the function g of x. So let me just draw here everything along this line is known. So along this line we have that f of x is equal to g of x. And apart from that, we have boundary conditions for x equal to 0 and x equal to L. So here we have our boundary conditions. So everything along this line and this line is known as well, where this is given by f right of t, and this is given by f left of t. Okay, and suppose we discretize our space-time domain, and we discretize it into a grid that has n+1 intervals along the x-axis, which means 0 equals x0 and L equals x n+1. We have n+1 intervals, each with equal length h, and then our time axis is our time interval from 0 to t is divided into m intervals. So big T corresponds to the mth point in time, whereas time 0 corresponds to t0. Okay, so now we have our grid, and now we just need to figure out, what do we know? Well, we know some stuff based on the boundary conditions. So if we consider the fact that we use the notation Wij to denote the difference approximation of f of xi comma tj, then we actually know the values of w0j and wn+1j for all j from 0 to m based on the boundary conditions. And we also know the value of wim based on our terminal condition for all I equals 0 to n+1. And note that normally we work with an initial condition here and then we work our way upwards, but in this exercise we actually have a terminal condition given, so we will be working our way downwards, which means that if we have any kind of update function, we're actually interested in wj, given that we know wj plus 1. So we will start out up here and then work our way downwards. Okay, let's take a look at what else we've got. What else do we know? Well, we also know the values of these coefficient functions. So let us also write that down. We know the value of mu and sigma square and r and eta. So we know these four values as well. And apart from that, we also know our time step length and the length of our step size and space. And apart from that, they say we can choose some theta and use that to construct a finite difference scheme. So let's just say we also know theta, and m and m+1 are also known as well because we choose them ourselves. So see, now we've written down a lot of stuff just to have some kind of overview of what's going on. And let's read the next part. On the next page, they say we can do some stuff, and then we can take our difference approximations and plug them into the PDE, move around a little bit, and then achieve this equation system where the coefficients are given by all of this. And then they ask us to write up the equation system for an arbitrary but fixed value of j as a matrix equation system. So you've worked a lot with matrix equation systems in the previous weeks as well. And from week 5 there's also a quick how-to video on matrix equation systems if it's a bit rusty. The main point here is not to get confused about what's going on and just keep asking yourself, what stuff do I know? What stuff don't I know? So, first of all, let's think about whether it's important that you think a lot about these coefficients. And the answer to that is no. You don't have to care about these coefficients at all, because the important thing to remember is just that you know the value of these coefficients for all I and all j, simply because mu, sigma square, r, eta, and theta are known. So we can just check these off over here. La 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 la. So we know the values of all of these coefficients. So it suffices to just look at this thing over here and think about how to write it up as a matrix equation. And when we do that, you may notice for I equal to 1 that then you have W0j down here and you have W0j plus 1 down here. And these are actually values that you know. And that holds for all j. So they address this in the exercise as well. The exercise actually helps us out a lot. They practically just give you the solution. Where they say, note that terms like this and this and this are known, so you shouldn't include them in the matrices, but throw them onto the right hand side in a separate vector. So you have a separate vector epsilon j and a separate vector delta j. So what is it we want in A? We want to write up a matrix equation system where the unknowns are the wj and wj plus 1, where you find wj based on the fact that you know what wj plus 1 is for j equal m minus 1. So just for comprehension's sake, let us try to write up what it is we want to look at. Well, remember that we had a terminal condition. Shouldn't have deleted that. We had a terminal condition up here. So essentially what we will do is we will start at j equal m minus 1 and then move our way down to j equals 0. So let's take a look. For j equal m minus 1, you have W m I minus 1 plus W m I plus W m I plus 1 with some coefficients in front. And we know the values of these. Yes, so based on the values of these, you can find the values of w m minus 1. And based on the values of these, you can find the values of w m minus 2, etc., etc., until you come down to w0. So this is how the calculations are gonna go when we consider j's. So how should the matrix equation look? Well, since we are writing up the matrix equation system for a fixed value of j, then the index that is the reason that we need to write up a matrix equation system will be I. So what will happen here is we'll have some kind of big matrix, an n times n matrix on this side, multiplied by our W1j, W2j, etc., etc. And then we'll have another big coefficient over here, and here we will have wj plus 1 instead, and then we will have some epsilon 1j, epsilon 2j, etc., etc., and then plus a delta 1j, delta 2j, and so on and so on. So you just have to figure out what's supposed to be in here, what's supposed to be in here, what's supposed to be in here, what's supposed to be in here. Take a look at the indices and think a little bit about it. It's not that hard. So this part is actually very simple. And if you have come to this step of the video and you're still watching the video and you're still confused, then it's probably because it would be a good idea to take a look at the matrix video from last week. Yes. So, this is just a warm-up for 6-2. Happy problem solving.